Hi, class. Welcome back. This is lecture 20, Learning-Based Motion Planning, with subtitle End-to-End Approach. So this lecture uh, material is relatively new, since end-to-end autonomous driving, end-to-end motion planning has only been, you know, has has a history of only about 4 years or so. So a lot of the contents are relatively new, and I had to put these together um, and try to deliver what has been happening in the academia as well as industry. Okay, let's begin. The outline is as follows. I'm going to give you introduction to E2E planning. And then I will cover some basic training methods, and then I will address challenges, and then additional topic on neural simulator, which is pretty one of the hot uh, research area in computer vision and AI community. So since E2E autonomous driving has short history, I don't have a lot of contents, or there's not much research output from the academia as well as in our lab. This is a very active research area right now, and I will mostly focus on problems and the concepts people are, you know, organizing as of now. So I hope it help you understand what's going on in the field. Okay, E2E planning. So why E2E? So as you can see here, x-axis is cost, or you can think of it as data, y being performance. Then rule-based algorithms usually give you decent performance with relatively low cost or low data. But as you collect more data um, and learn properly, then learning-based approach can actually overcome traditional algorithms. So, and there are more details. For example, for E2E planning, planner can continuously learn from data and evolve over time, which I sort of explained in previous slide. And second, you can avoid or mitigate information loss from post-processing steps in perception and prediction modules. And you can also mitigate compounding errors between module tasks from the upstream to downstream. And then by using neural network, uh, clearly we can do parallel computing. We can take the advantage of using, TPUs or accelerators. Whereas if you use optimization algorithms, you just need to you have to solve it iteratively. Okay. However, E2E also has some challenges, many challenges. One is interpretability. The other one is causal confusion. And there are actually a few more, and we'll talk about that. Um, to to give you more introduction on the architecture, um, classical planning has been designing planner using perception results, and future trajectory or of surrounding vehicles and pedestrians. So to actually make this clear, you actually need these information too. Okay? Um, by the way, end-to-end planning, end-to-end uh, planning is not completely new. So people actually have been investigating this, uh, you know, long time ago. Not too long, but about a decade ago. But it did not quite work back then, and that's because people were trying this very simple, architecture. You just put all of the sensor input to the large neural network, and you know, and have the planning output, um, and do the feedback, and hope it works. But it did not quite work for multiple reasons. Model, learning methods, um, and the architecture, and so forth, which we'll discuss in the following slides. But current trend, current state-of-the-art, architecture looks more like this. So we have feature extractor, just like perception feature extractor. And then we have multiple heads, perception head, prediction head, planning head, and they're sharing the feature from the feature extractor. And planning is also getting the feature as an input, and it's trained either sequentially or in parallel with other heads. And the model architecture looks something like this. So why modular E2E planning? Um, by um, by having this architecture, modular um, architecture, we can actually have some benefits listed here. So, for example, intermediate task provides additional interpretability or reasoning. So, for example, if we train perception head and prediction head, and then we can actually use that as interpretation or reasoning of why planning output is um, uh, outputting that trajectory or actions. And we can actually use it output of prediction head or perception head, or just use it for interpretability or visualization. And second, this is very important. We can use multiple heads to generate multiple gradient information to train feature extractor. So if you have only one planning head, it may not give you enough information uh, to train the feature extractor, which which makes it difficult to make the feature extractor generalize for many different environment, corner and edge cases. So, and by having this architecture, we can have feature sharing as well. So these different heads use the same feature. Okay. Um, what about input and outputs? So inputs are obviously sensor inputs, but in addition to images and vehicle states, we also need navigation inputs, vehicle kinematics, um, and here it says HD maps, but usually we need at least SD maps, standard definition maps for navigation. If, of course, if you have HD map available, then it'll be very helpful, but usually mass production vehicles um, are not equipped with, HD maps. And then on the other side, output side, we have multiple options. We can consider multiple options, and people can consider outputting uh, control commands such as acceleration and steering, or you can generate or output trajectories, waypoints, which is more easier to interpret. It's more intuitive from a human uh, perspective because it's in space, and you can do safety checks, feasibility checks, and so forth. And another output would be trajectory candidate scores. So for instance, if your output has multiple trajectories to to make sure you have diverse uh, output candidates, trajectory candidates, then eventually you need to select one, you need to make a decision and select one trajectory to execute that plan. So to do that, you would need some sort of score for each trajectories. You can also see that as confidence or likelihood. Um, how likely is this trajectory, considering if human was driving. Okay. And let's talk a little bit about architecture. So this is history in academia. So people have been using um, various types of architectures. So people did try, um, combination of sequential and parallel architectures. But recent trend has been moved to parallel architecture for uh, for the heads. So mapping, motion prediction, occupancy prediction, and planning. So these are considered as parallel heads, parallel decoders, and just directly receives features. So that way, the architecture is simple. It gets, the full feature information it needs, um, and training becomes, you know, simpler compared to previous ones, um, and so forth. So here we have, um, so here are some popular models: UniAD, VAD, and ParaDrive. Um, and uh, we listed those papers here. So VAD um, basically does, so if you go back, BAD has mapping and motion planning handles that as a sort of sequential manner, and planning gets information from those two modules, and you can see that here. Um, so it gets, more information, more semantic information, rather than just raw features. Okay. And then if you look at UniAD, um, it does similar things. It has perception head and prediction head, and the planning module receives, you know, some of the features you get from these, you know, perception and prediction heads. But when you move to ParallDrive, it's completely parallel architecture. So you have one feature extractor, and you have multiple heads, decoder, mapping, prediction, planning, and they share the same queries and features. No, they do not share queries. They share features, but each decoder, each head has its own queries. And for training purposes, all of them are used. But when it comes to, you know, uh, taking action for driving, obviously you would use planning head, whereas other modules are for training purposes, interpretation purposes, and training the backbone, the feature extractor. Okay. So this is not um, so this is what has been happening, but I think there are still room for improvements, when it comes to architecture. Um, so you can think about it. Okay. And let's move on to next topic, which is training part. Uh, the end-to-end autonomous vehicle, autonomous driving, end-to-end model is somewhat misleading. I'm saying that because if you simply say end-to-end um, model, then it sounds like you can train the whole thing, whole model, end-to-end, uh, in a single stage. But in reality, um, it 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 needs to be trained multi-stage. For example, this is an example. And in fact, end-to-end became um, possible, I think, because we already have feature extractor that has been trained in the previous years. What that means is, in the early stage of autonomous driving studies research, people have been focusing on how to train, the perception uh, model, which includes both feature extractor and head. So, and if you look into how language models train their large language models, they actually have multiple stages, and it's called pre-training and post-training. I think that we need that type of training process for robotic systems as well. And for example, here we can train feature extractor using self-supervised learning, data with no labels, and then we can you know we can label data, and do supervised learning with perception head, prediction heads. And then we can do second training, and then um, we can train planning decoder, planning module. Um, but how to train planning module or third stage is still ongoing active research. Um, and we'll talk a lot about this in the following lecture notes. All right, training methods. So there are mainly two approaches. Learning from real data and learning from simulation. Supervised learning and reinforcement learning to train the uh, more E2E planner. Okay, this is supposed to be E2E planner. Okay. The supervised learning, it's often called imitation learning or behavior cloning, and that's because we are we if we train the model using real data, it's usually the data is human driving data, human driven data. So basically, if you use supervised learning using human driven data, then it's sometimes called expert driver. Then it's behavior cloning, imitation learning. Whereas if you use RL, then you have to use simulation, and you get feedback from the environment, the simulator, and using reward feedback. So those two are two main training methods. And this is so if you look into imitation learning, there's naive behavior cloning, and then there's a method called Dagger, data aggregation. So naive behavior cloning, um, what it's doing is it uses L1 or L2 loss between the ground truth versus output trajectory. So, and then you do backprop to train the model. But this has many issues because first of all, the data has biased. The human driving is very biased. It doesn't cover a lot of the scenes. It doesn't cover a lot of um, you know decisions, different decisions that are covered or are very risky corner edge cases. Those are very rare data. So it's very biased. It's also known as long tail problem. So when you actually use only those data, uh, it leads to many problems. I will talk about that in the following slides. And to mitigate that problem, people have proposed a method called Dagger. What it does is you train first, and then you update data with trained policy, and which is going to generate um, you know new data, and then you can train new policy with updated data. So that way you can um, you know avoid a little bit of overfit and make the data a little more diverse. So you can improve the um, naive behavior cloning method. So here's the issues with imitation learning. Um, First, distribution shift. Predictions affect future inputs, observations. Small errors in predictions can lead to new states not available in the data set. So for instance, if you collected data using expert driver, you only have data from these trajectory or from these scenes. But if something happens to real system, real world, and if it goes slightly off track, then it's going to be um, unseen input, and the model will not be able to make decisions, proper decisions. Okay, will not know what to do. And second, causal confusion. Um, Model misidentifies the wrong cause of an action. For example, brake indicator leads to braking action um, in front of pedestrian. For example, if there's a obstacle and the model brakes, but it's not clear if the model made braked because there is a pedestrian, or you are braking makes the pedestrian appear. Okay, so causal, so reasoning, causal, interpretation, they're similar, related terms. Okay, and the long tail distribution in data, basically, um, is the biggest issue. Here's some more training methods. Just trying to you know make you familiar with some of these terminologies. There's a method called inverse RL. So if you look into optimal control field, there's inverse optimal control. So what it does is optimal control requires cost function designed by engineer, and then optimal control algorithm will solve for solution that minimizes that function. In the inverse optimal control problem, you need optimal solution. The optimal solution is available, and then the objective is to find the unknown cost function. And IRL is similar. So for RL, you need to design reward function, and then you will learn policy. Okay. But in the case of IRL, um, you assume, so you need expert policy. You need solution, um, and you want to learn the reward. Okay. And so, by the way, usually, so you, so expert policy is usually um, either designed, or you can couple the policy, the optimal control with a data. So that way you can provide sort of expert policy in the form of data for training or finding the reward function. Here's more details about inverse RL. Um, if you're interested in IRL, you can take a look at some of these papers. Basically, what IRL does is um, it mitigates some of these naive imitation learning methods, because instead of learning the policy directly, if you can learn the reward, then um, then you can use that with some optimal controller that you can design based on the reward. And then if you do so, it's usually it provides more robust performance compared to simple imitation or behavior cloning methods. So people have been investigating into IRL. Okay. And of course, RL is popular method because it looks for the policy, optimal policy directly um, from experience, from exploration. So, but to do that, to explore and to experiment, um, you have to have environment. You have to have, more specifically, you have to have simulator, basically, to get that feedback. So for gaming problems, this is this is not perfectly fits because for gaming you're already in sort of simulation environment. Um, so RL has been very successful in gaming problems, game and chess, uh, you know the game of Go, AlphaGo, blah blah blah. These game problems, they have sort of you can create this environment that are identical to the um, real environment because it's virtual already. But this becomes a big problem for robotic systems. I will talk about that later. Okay. But anyway, so if you're going to use RL, you need to have a simulator so that you can, try different actions and get feedback, reward, and explore different state space and different action space. And the goal is to find the action or policy that maximizes the reward. So you have to design reward too. So you need a simulator and you need the model, you need a reward function. And then when it comes to model, there are two branches, model-free RL, model-based RL, and for model-free RL, there's deep Q-learning, policy optimization, or proximal policy optimization, soft vector critic. People are still trying different methods, but PPO, proximal policy optimization, and soft actor critic are two popular methods for robotic systems. Um, um, yeah. The model-based RL learn the environment model in addition to training the agent. Okay. Here's the limitation of using RL. Like I mentioned before, it requires simulator. Um, and RL is sample inefficient, meaning that it requires many interactions with environments. But it's but it's okay because simulator, if you can accelerate simulator, and if you can automate all of this learning process, then computer will do the job, right? Although it may not be so efficient. Um, and second, RL requires interactions with the environment, so you have to have a simulator. For example, for safe training. So in real world, we cannot really uh, create collision data intentionally, right? We cannot explore that kind of uh, you know scenes and scenarios, but simulator can. Um, and this is the big problem we need to solve. Sim to real gap. So there's a simulation, which is not identical to real world in different aspects. And I'll talk more in detail in the following slides. Okay. Okay, let's talk about challenges in end-to-end planning. The main challenge is the data. The data is extremely biased, um, meaning that if you just collect data without careful designing um, the data set, then you're going to collect very similar data, very boring, normal driving scenes that are very redundant. Um, but there are almost infinite number of corner and edge cases and you know interactive between multiple agents or very risky collision scenes also needs to be collected and trained to properly to train the model. So to do that, there are two methods. One is data engine, data flywheel. So this is how Tesla approaches. So it uh, using data, it train the model, deploy, and then um, using sort of ghost mode, you can kind of mine data that doesn't work quite well, and then you can use that sample. You can boost those data, meaning that you can collect more uh, data that are similar to that specific scene or scenarios. And then you need to label and train the data. So this is how Tesla approached. Um, and this is possible because they have a lot of resources. They have vehicle fleet, most of all. So to be able to do this, you have to have vehicle fleet to mine and boost data that you need. Um, and another method is simulator, which you can generate data, right? Which is much cheaper, faster, easier to generate. So it sounds so good, but it has other problems. Okay. Um, so RL versus imitation learning. So we talked about RL, introduced RL and imitation learning, supervised learning. And RL has potential to complement imitation learning to resolve the covariance shift problem, meaning that we from the biased data, we have very limited data that are in distribution um, here. And it doesn't have sufficient state and action space coverage, not enough exploration. So an RL can actually complement, you know, these limitations of imitation learning. So people have been trying, combining RL and IL, or use RL to augment IL for faster training. And you will be able to find some studies, you know, using RL in addition to IL. But the biggest problem with RL or simulator is the sim to real gap. There are mainly three types of sim to real gap. First one is perception gap. Second is agent behavior, unrealistic agent behavior. And third one is dynamics difference. Um, in many robotics studies in the past has been focusing on this sim to real gap, and um, so meaning that they would train their um, their policy in simulation environment and focus on mitigating sim to real gap uh, in terms of dynamics difference. Because for robotics, that has been one of the main challenge. But autonomous vehicle, for autonomous vehicle, these two are bigger problems rather than the dynamics difference. So we need to worry about these two sim to real gap. And another problem we have to worry about is evaluation of the model. If you have modular approach where you have perception model and then traditional planner, you can evaluate your perception model, and then you can evaluate um, your planner using simulations, and then you can evaluate your planner uh, in real world with you know some scenarios, uh, corner cases that your planner may not be able to work, because you understand how the planner is working, you can actually design these scenarios to test the vehicles. But when you move to E2E, um, there are two evaluation paradigms in academia. Um, the first one is open loop. The second is closed loop. The what open loop evaluation means is it uses log data and see how close the output is to the human driver actions or trajectory. Um, and that's how we trained, right? Supervised learning, L1, L2 losses with trajectory action sequence, and we are evaluating in the same manner. But um, but if you actually close the loop, um, meaning that you actually run the model in real world, it's going to behave very differently. Um, and and there are multiple reasons. There's a lot of real world uncertainties, modeling error. Um, there's a lot of disturbances. blah blah blah, right? So, and if you go off track, or if your covariance has some shift, then your model may not be able to perform or come back to the you know the proper trajectory. Okay. So usually it does introduce problems when you go closed loop. But the closed loop is the proper and the only way end-to-end model can be evaluated as of now. So think of it, if you think of testing your closed E2E model in real world, it's going to be challenging, right? It's very time consuming and can be risky, um, and a lot of real world testing, which um, is labor intensive, time consuming. Um, and closed loop real world evaluation can lead to collisions, um, which we can't accept, right? Um, and then another challenge is diversity in planning. Um, I talked about bias data. If we have bias data, that means our output will also be biased unless uh, we have a diverse data, data with enough diversity. So we talked about data engine, um, but is it guaranteed uh, that we have enough diversity? And can the model generate planning output that are diverse enough? Okay, so that's another challenge. So let me move on to the last section, which is neural simulator. So to solve these evaluation problem and data problem, um, and sim to real gap problem, um, we can use simulator that are, you know, very realistic, okay? But traditional simulators have a lot of sim to real gap. But what if we can come up with a simulator that are so real that it can almost replace real world? Okay. And this is one of the hot, topic, people are looking into these days. So I talked about bias data, long tail problem. So to solve that problem, we have two approaches, data engine and simulator. But data engine requires vehicle fleets with a lot of resources. Whereas simulator is, cheap, easy way to generate data, but it has, sim to real gap. But we can, if we can use a simulator, and then we can train this RL planner very efficiently. But then the problem is we cannot use that we cannot use that RL planner for E2E planner because it has two different inputs, right? Um, the E2E is supposed to take feature as an input, whereas if you use simulator to train RL planner, then it takes state as an input. A simulator cannot really generate features, right? Um, but what if we can? Can we make it? Can we make the simulator generate features? Okay. So that's a question you might want to ask. And so if we, anyway, so the point here is if we can use simulator and reinforcement learning, we can train planner very efficiently, but then we will have to somehow transfer that knowledge. Okay. So we talked about closed loop evaluation, um, which requires real world implementation and testing. But what if can we replace the real world with the simulator? Then the closed loop testing evaluation becomes so much easier, practical, um, and so forth. So we want to come up with simulator that are so real that it can replace the real world, right? So here's the simulate neural simulator. You know, I have been picturing. I have proposed. Um, so this is a figure um, I started to organize. You know, the, the problems, the ideas in academia. So here is the E2E planner. We have feature extractor and planner. And then we have a simulator here, neural simulator, where we have physics engine and rendering engine. So traditional simulator also has physics engine and rendering engine, but here we are considering replacing that physics engine and rendering engine with neural engine, neural physics engine, neural rendering engine. And then if we have neural simulator, we can um, we can train we can train the state-based planner using reinforcement learning, and um, and then there are you know many ways we can use this planner or transfer knowledge from this planner to end-to-end planner. Okay. Because the neural simulator can output photorealistic images, um, we can put that into perception model, then we can generate features, and then we can actually use this feature to train the planner instead of the state. Okay. Or um, just directly yeah, just directly use that feature to train the planner, and then we can use this planner as E2E planner, right? But of course, there's a sim to real gap here. Although this image may be very photorealistic, it's probably not perfect. So there's a sim to real gap there. But the problem is how do we come up with a neural simulator, right? Is physics engine can simulate real world? Can rendering engine render images that are real? So those are active research areas. And to do that, we need large data set and to train the neural simulator. Okay. And for both neural physics engine and neural rendering engine, um, uh, you it's likely that you need both uh, a generative model to generate, scenes and generate images. And especially for rendering engine, you would need, NeRF or 3D Gaussian splatting um, methods to generate photorealistic images with 3D consistency. Okay. So that brings us to world model. So world model is a pretty hot keyword these days. And it's used for many, many applications, not just, autonomous driving, but world model you know, can be used for virtual space, uh, like I said, virtual space, for gaming, and so forth, or to to um, to replace real world like we need, or like a simulator kind of thing. It's very similar, just different term, from different perspective, different society. If you look, you can see it's very, similar thing. So if you take a look here, we have these variables as is seen, or you can think of it as state. There's action, there's observation. You can think of that as images in the case of our problem. And then H represents horizon. And then the world, what world model does is it predicts future scene given past information and current actions. And this can be, realized, applied to latent space, state space, image space. Okay. So, um, and this is mathematical description of that definition. Okay. And this figure is an example of different world models. Here we have latent world model. We have image world model, or image generation model, or a video generation model. And then we can also have state generation models, world models. So for given action and observations, what's going to happen to the world in the next time step, future. So that's basically what simulator is doing, if you think about it, right? So with if world model can really replace, mimic real world, then we can use that as a simulator that can replace the real world, and we can use it for training and evaluation, testing. Okay. So I think this will be it for today. Um, thank you for your attention, and please ask questions if you have any. Okay. Thanks.